Hi everyone, good afternoon. Welcome to the Formal Methods and Software and Architecture session. Today we will have a keynote speaker and then 3 minutes pitch talks. The odd number speakers will be here and the even numbers over there. And then the interactive session will be tomorrow. So now it is my great pleasure to introduce to you our keynote speaker, George Papas, who will give a talk on formal methods in robotics. Thank you.
Thanks, Jana. I'd like to thank the organizers for the invitation, as well as the current and former students that actually are primarily responsible for the work I'll talk today. In order to motivate the work, I'd like to place it in the context of some hierarchical architecture you'll find inside a typical multi-robot system. So at the lowest level, you would have quad rotors in Vijay's lab. And then at the layer above, immediately layer above, you would have some kind of embedded processor integrating the sensors, controllers, actuators, and so on. The layer above would be the MATLAB layer, where you would be doing your signals and systems. You'll be designing controllers, filters, estimators, and so on. And then the layer above that would be your supervisory logic, your high-level planning logic, and so on. And the objective you have to do, I mean, we have a lot of very good theories in trying to understand any particular layer, but what is sort of missing a little bit is understanding a little bit the more holistic design, as well as more cross-cutting issues across the layers. So this motivates a little bit the talk. So if I were to abstract a little bit out of from the architecture, I'll be thinking about 3 layers. The layer at the bottom would be some form of real-time computing, which actually I'm not going to touch at all today. The middle layer is the MATLAB layer, where we design controllers, improve stability, and Kalman filters, and so on. And then the highest most level is where you would have some high-level planning, supervisory logic. And at that level, I'm going to be advocating the use of temporal logics or some form of a formal mechanism like that. And again, even though there are interesting problems at each individual layer, I think we have to start paying a little bit more attention on the interfaces between the layers. So for example, at the bottom 2 layers, there are interesting issues of how to think about, say, controller sensing over new real-time computing paradigms. And then at the highest 2 levels, you should think about, for example, I'll be talking about today, is how to think about temporal logic control of more dynamical control systems and so on. So the whole session is on formal methods. I think it's good for everyone to have some context about temporal logics. So the way we'll be using temporal logics today is to sort of describe formally missions. So the idea is here that you have some kind of a robot, you have an environment, which for today is known, we have rooms, and then we would like to do some kind of a high-level plan, and the high-level plan is, for example, visit the encircled areas, avoid some corridors, and so on. So the question then is how to specify, even formally, such a plan, and then how to go all the way down that hierarchy, down to the robots, and so on. So to specify such tasks, we have been using temporal logics, and you can specify a lot of common tasks, classic robotic tasks, such as so the diamond there stands for eventually. So eventually you'd like to go to room P2, but now you can start building a little bit more complex tasks. So you can say you eventually go to P2 and P3 and P4, so you can think about coverage. You can do sequencing requirements, and you can even write using the so-called until operator, things like go to some place, and until you go there, avoid obstacles. But the most important thing, even if you don't want to use temporal logic, you can design your own mission logic or mission descriptor programming language. The most important thing is that whatever mechanism you use, it should be formal, so it has mathematical semantics, and it's compositional, meaning that you can stitch smaller tasks in order to build larger tasks. So you can write larger specifications by simply using basic Boolean and/or temporal and/or spatial operators, but it's important for your mission description languages to have some form of compositionality. So temporal logics is one such mechanism, which would allow you then to write things like this, as we were describing. For example, visit a few rooms while avoiding a particular corridor, and later we may also use some kind of sensor logic where we can say, if you see something, then you may want to go somewhere, and so on. Okay, so the basic problem then is if somebody gives you such a mission in a temporal logic for this talk, and somebody has some kind of dynamics, let's assume fully actuated, but of course one can do a little bit more general. The idea then is how to design a controller C, which when you compose it with a robot R, satisfies the formula phi. This is the sort of the logician's way of saying satisfies the specification. So our first attempt in this problem here was to use the classic model checking. You can view this as a model checking problem in the formal methods and the computer-aided verification literature in computer science. And the way that you would convert a planning problem into a model checking problem would be as follows. Since the environment is known, you could potentially discretize it, in which case you would get a whole bunch of cells. The cells would automatically give you effectively code, and this code gives you the adjacency, the spatial adjacency relations from one place to another. You take the temporal logic in this sort of formalism, and you convert it as the specification. And this is written in a very well-known toolbox known as a new SMV. And then effectively what the model checker will try to do is it will try to find an execution of this program that actually meets the specification. Okay, so you've converted a planning problem into a model checking problem, and then eventually the model checker, which is a bug finder, which is used for testing software, has found a sequence, an execution of the code, a sequence of triangles in this particular case that says that if you follow this particular sequence of triangles, you will in fact meet the higher level mission. Okay? Now, of course, it could be that this mission was impossible, in which case you would have gotten empty, nothing, which is bad news for planning, but it would be good news if you were testing software. Now, of course, then you still have to deal about how to take the sequence of triangles and execute that at the lower level. So the good thing about the model checking is that there are powerful tools like NewSMV and Spin, which you could, so you could scale up to relatively large state spaces, even though formally, theoretically, this problem is exponential and very hard. The disadvantages is that the previous approach was effectively something like an open loop approach, which was basically saying, given its specification in a temporal logic, figure out an open loop path that would meet the specification. So there was nothing really reactive or closed loop about it. There was no interaction with the environment. It's not that we were sort of sensing something and based on that we were reasoning about something else. There was nothing reactive, there was nothing closed loop, which led sort of to the subsequent paper with Hadas and Yorgos on reactive LTEL planning. And here we took we looked at, we wanted to introduce first sensing and reactivity. So what we did is which was known as, we broke up the formula into two parts, one that had environment variables and one that had variables that had to deal with a robot. And the idea here is that you want to be able to reason that if the environment satisfies a certain property, then I will be able to guarantee that the robot will meet a spec. So later we'll give you an example that if there is a parking lot available, and that's an environmental assumption, then I should be able to prove that the robot will eventually go and park. Okay, so there's a certain assumption about the environment, and you can now reason about the environment in a formal way. But there's also one more restriction, and that is that the formulas, both for the environment as well as for the robot, satisfy a certain syntactic structure. So we're not looking at the full-blown LTL, but we're looking at a weird substructure, which we don't have to get into here. But the important thing about this substructure is that it actually makes the problem more computationally feasible. So here you can look at an example which in English would be written as a scenario that you're searching for Nemo, and you may have some a priori knowledge about where he may be. And then you would like to search, so you have a binary sensor that tells you whether you have seen Nemo or not. And then you have a certain, you have robot states, which could be the cells in the environment. And then you can express this, hopefully in an automatic way, into a very complicated formula, which at some point you shouldn't have to get involved, but it is important for this to be there, and it is important for this to be mathematically rigorous. And now the question is, can you find trajectories or plans or closed-loop controllers that would meet this complicated specification? Okay, so the reason we are restricting to this particular fragment of linear temporal logic, which is known as general reactivity 1, is that because for full-blown LTL synthesis, is doubly exponential in the size of the mission, in the length of the formula, whereas GR1 is actually polynomial in the number of states, but the number of states, of course, may themselves be exponentially the number of variables, but it is a significant reduction if you would like to get to more complex missions. And the way you should be thinking about this and the way this is actually solved computationally is as a game. It's a game between the robot and the environment, where the environment makes a move and then the robot makes a counter move, and the robot is trying to meet the specification regardless what the environment does, as long as the environment stays within the assumptions that we have modeled. If you don't know anything about the environment, you can say you can put the Boolean formula true, in which case you have to win the game no matter what the environment does, and of course that will lead to a much larger controller. So the more you know about the environment, the more you'll be restricting effectively the search space in trying to get a reasonable solution here. Okay, so there is some loss in expressivity. There are certain things you cannot capture in full LTL. But the important thing from a modeling standpoint is that there is a clear separation in the mission about what we are assuming about the environment and what we are assuming about the robot. Now, given these, using this formula, Nir Peterman and Amir Pnoeli, Amir Pnoeli actually received the Turing Award for introducing temporal logics in computer science and programming. There are automatic ways of synthesizing an automaton. If you're in computer science, you would call it an automaton. If you're in the AI community, you will call it a planner. And if you're in the control community, you would call this a discrete controller. So the idea here is you write a specification and you press a button, and all of a sudden you get, after the algorithm runs, an automaton that realizes the specification. So this is, rather than planning by model checking, this is planning via sort of controller synthesis. So rather than doing the design first, verify second paradigm, which has been the classic paradigm, the idea here is specify first and synthesize second. Okay, so you synthesize a discrete controller, which automatically, if the specification is satisfiable, you would get automatically this the software effectively that meets the specification. Now, this is of course still the discrete controller. It's at the discrete level. We still have to deal about how we're going to transition this at the continuous level. Okay, so we still have some differential equation somewhere down there, or discrete time system or something. So we still have to map this to a lower level. Okay, so this leads effectively to fundamental problems in what a lot of people in the hybrid systems community are looking at. And the idea there is that you have a differential equation on the left, and what you would like is to extract some kind of a discrete abstraction on the right, the green automaton, so that you can design then an automaton, a controller automaton, which meets some kind of the specification, and then you pull back and you refine the discrete solution back to the continuum, and you get some kind of a hybrid controller. This is a problem that has a history of at least 15 to 20 years now. And now the idea is, what is the notion of equivalence between the discrete and the continuous? And this is the notion the notion that is relevant in this particular context is the notion of bisimulation. And bisimulation means that the continuous and the discrete systems are bisimilar. And the thing about bisimulation is that if two systems are bisimilar, then they satisfy the same temporal logic formulas. So if I can show that the system on the right, the discrete abstraction, satisfies the temporal logic formula, if I can show that the continuous and the discrete systems are bisimilar, then effectively the continuous system will also satisfy the same. So how would you design then, how would you do this? And the way that we were going to do the refinement is somewhat obvious in this context. The idea here is that if your discrete layer tells you go from this room to that room, then what you need are controllers that basically, regardless of where you start in the room, will enable you to make this transition. So you have to have the ability to implement the discrete action regardless of how you start at the layer below. Okay, so if you want to do it with this approach, this is the kind of thing that you would need. And there are controllers out there that design vector fields or design controllers that have this shape. And for example, Colin Belta has been designing such controllers, and David Connor, with how we chose it and so on, they were designing such controllers. And the sort of the cascaded Lyapunov functions have more or less the similar spirit. So then the idea is essentially to compose these controllers in order to meet then the higher level specification. And effectively, this is what you would do. So you synthesize the automaton first, and then when you go from room 1 to room 2, you have to embed these controllers in each of the discrete modes. And at the end of the day, what you're going to be left with is a hybrid automaton, because in each mode you're going to be having some kind of a vector field, and you'll be having switching conditions. And this hybrid automaton effectively, by construction, will meet the higher level specification, the higher level mission that you would like. Okay, so this is summarizes effectively the approach, that you start with a formula, which in this GR1 fragment. Then you synthesize first the discrete controller P that meets the specification. And then what you do is you design a hybrid controller H, so that when you compose it with a robot, it's bisimilar to the discrete system P. And since P satisfies the mission, then the continuous system will satisfy the mission. That's basically it. And at the end of the day, the guarantee you get is that if you can synthesize the controller and you can design continuous controllers, then you will meet the spec as long as the robot operates in an admissible environment, meaning that as long as the robot operates in an environment whose assumptions you have modeled in that formula phi. If the robot does not operate in such an environment, that's an implication, all bets are off. We cannot really guarantee anything. Okay, so this, in a couple of case studies in collaboration actually with Howie and David Connor and Hadass, we had looked at the valet parking example, and the kind of missions you would be able to describe here are DARPA Urban Challenge-like missions. So what you would want to do is drive around, go in front of a restaurant, and then ask the car to go and park itself. So you would want it to meet the kind of traffic laws, and then if it finds a parking spot it should park, it would invoke actually the parking controller and park, but otherwise it would have to keep on searching forever and so on. And even though these are challenging problems from a computational point of view, things scale up to the point that, these kind of problems would be viewed as reasonable from a synthesis point of view, and you can sort of see the scale of the problems that we have. What we're going to talk about next today, one of our postdocs will talk about is a slightly different approach. What I presented previously was a little bit of a top-down approach, that you start with a mission, then you refine to the discrete level, then you refine to the continuous level. This is a very top-down approach. If your physics below is very constrained, this is not going to work. So this is a little bit of a different example where, rather than going top-down and designing controllers, here the idea is that somebody, in this case Vijay's group, is giving us a library of controllers, and they say, here's a library of motion primitives that we have available, and the idea then is how to compose the motion primitives in a way that we can meet a higher level temporal logic specification. Okay, so here there were some, the Internil later will present a little bit more what. Now the community has developed quite some tools, some of that you can use. Some of these you'll hear about later today. Some of these are also becoming ROS compliant, so you may be able to use them in your labs. There's quite a few opportunities, I think, for the community, and I know many people are pursuing these, and you'll hear about these later in the session. It's important to have formal semantics and compositional semantics. One of the reasons is that it's an easy way to connect to computational linguists. So if you eventually want to speak to cars, and you want to, then I think it's a lot easier for computational linguists to connect to some representation like temporal logic. Temporal logic is clearly not sufficient for all the kinds of things you want to say, but it is a way of sort of showing how to connect the logical and the continuous. What I presented was offline. So you design the controller offline, and then you execute. that you'll hear later today, and there have been quite a few approaches of online sort of synthesizing these controllers in a receding horizon like way, and you'll hear from others today. What I presented, of course, was also deterministic, and there have been probabilistic versions of this with probabilistic logics and more stochastic dynamics at the bottom. And again, there was this distinction between what I was presented before was more of a top-down approach, but I think we have to also start thinking about more bottom-up. That's going to be very important, I think, for robotics, because a lot of the physical problems in robotics are going to be very, very constrained. And finally, I think at the end of the day, the most important issue here is connecting the signal to symbol in a very robust manner. And with that, thank you for your attention. Thank you.
Hi, my name is Matanya Horowitz, and I'm just going to cover some work I did with my collaborators, Richard Murray and Eric Wolf. What I want you to keep in mind is sort of our goals in using these techniques, and what we'd like to be able to do is solve sort of temporal problems for extremely large degree of freedom robots. You can imagine things like robots climbing ladders. You have a temporal sequence that really needs to be solved in a specific way, and so you have very hard constraints over the system passing through different areas of its state space in certain points in time. The difficulty is, we just had an excellent sort of overview of how these problems are solved, and usually you partition up your state space into some sort of MDP and combine that with your automaton that represents your specification, and what you get is sort of this huge thing, and there's very established techniques for solving these problems, but the scalability can be pretty bad. And basically, you're not only subject to the curse of dimensionality, but the curse of dimensionality with your specification, so it can be really tough. And so what I'm going to talk about is a way to avoid doing this, to avoid combining sort of things with and creating this product automaton, so you don't have to have this lifted system. And so why should you listen to me for 2 more minutes? I think we have some interesting ways of looking at this problem. We're going to not create this product MDP. We're going to combine solutions to optimal control problems, and we're going to get optimal solutions by doing addition. So that should be a little bit surprising. You shouldn't be able to do that, so hopefully you'll be interested. And we're going to use PDEs to solve our LTL problems, which we think is pretty interesting. The base we're going to take is actually at the Hamilton-Jacobi-Bellman equation. If you don't know what this is, it's basically a potential function, but it's sort of the best one you can get. There's some recent work that simplifies down the HJB into a linear PDE. Usually it's a nonlinear PDE when you have a couple of assumptions, and you can talk to me about what those assumptions are. And so a linear PDE is much easier than a nonlinear PDE, and I think this is a great insight, not due to me, due to some others, that we can really take advantage of. In particular, for this application, linear PDEs obey the principle of superposition, and so we can add solutions to create solutions to different problems. Very simple, but let's see how that can actually affect us in this context here. And our automaton, when we create the product, when we create the specification automaton, we can actually examine sort of what happens when we're in one state of this automaton. And what you actually have is a reach avoid task. So the automaton's telling you avoid these states and try to get to these other goal states. And so when we solve these problems over these huge specifications, we have lots and lots of these problems. And so what we do is we create primitives. We solve these PDEs over individual regions of the state space and then combine them at basically 0 cost using nothing but vector addition to solve a different PDE, which is the particular reach avoid problem. And so, yeah, penalties and goals. So here are examples of some of these primitives. We might want to visit these 2 regions or avoid them, whatever. So we can create the primitives, and we can actually get really rich behavior just by doing addition. And so what you see is some results of that. There's an exponential scaling in there. That's how you get sort of this richness. And we can use tools from PDEs to solve all these kinds of problems. Here's some examples. Please talk to me more.
Okay, I'm going to talk about formal verification of maneuver automata for parameterized motion primitives. My name is Matthias Althoff. I'm from Technische Universität München, and this is joint work with Daniel Hess and Thomas Sattel, who are from Technische Universität Ilmenau in Germany, and Daniel is now joint DLR in Braunschweig. So this talk is going to be about guaranteeing safety of robots that try to track a reference trajectory. Like in this example here, we have an automated car that likes to avoid this obstacle. So one thing, a naive approach of checking collision freedom would be to select a finite number of times and then check the occupancy of the vehicle at each time step, and then check if there's a collision or not. The problem with this approach is, first of all, you only have a finite number of times that you check, and the second thing is, usually if you have a tracking controller, you always have deviation from your reference trajectory. And that's because, first of all, you have uncertain initial states, uncertain measurements, and disturbances acting on the vehicle. So what we are doing is we don't compute only a single solution of our system, but we compute a set of possible solutions called, which is also referred to as reachability analysis. And in order to illustrate reachability analysis, we kind of project the whole state space in this figure just on the positions of the vehicle. So you can see then here, if you want to follow this reference trajectory, you don't perfectly follow it, but you have some deviation. But in order to compute that, you need the full vehicle model and the controller model, and you also have like states like yaw and slip angle and things like that. Now, if you then compute the occupancy of your vehicle, you realize, of course, the occupancy has increased because of the consideration of uncertainties, and the path that would have previously been assumed to be safe is now becoming unsafe. So our objective is to guarantee safety when all these uncertainties are properly considered. And again, the difficulty now is that computing these reachable sets takes some time. Currently, we can compute it like in the time that is required to perform the maneuver. But the idea to speed this up is to use motion primitives. You also heard about this in George Papa's talk. The idea is you have a set of predefined motions, like here this right turn or this turn that is a little with a smaller curvature. And what we do for each motion primitive is, we compute the reachable sets, indicated here by this dark gray area, and we also store the occupancy of the vehicle when it would follow this motion primitive. And what we then do is, we always have an assumption on the initial set of states and then a final set of states, and then we check if the final set of states is enclosed in the initial state of the next motion primitive, so that we can connect our movements. So the next one I skipped. This just shows the integration of this approach in collision avoidance systems. Just like to talk about the main benefits. So we compute all behaviors, we consider uncertainty, and we can prove correctness using motion primitives. Thank you very much.
Good afternoon. I'm Michele Coledanchise, a PhD student at the Royal Institute of Technology in Stockholm. I will be presenting you the work I've done with my supervisor in how behavior trees modularize stochastic robustness and safety in hybrid systems. Behavior tree is an action plan framework that has been inherited from the artificial intelligence plan in computer games. And they've been very popular since they provide a good balance between goal-oriented behaviors and reactive plan. And they've almost completely overtook the finite state machine in the high-profile video games in the market. But to understand the advantages of behavior tree over the finite state machine, we have to realize a few things. First of all, an action plan is generally described by a finite state machine, which is built on transition. These transitions are the one-way control transfer and are very similar to the go-to statement that we had in computer programming. But we got rid of the go-to statement in computer programming because they were too primitive and too much an invitation of making mistakes in the program, especially when it comes to make a very complex one. And we have overtook the go-to statement with a two-way control transfer, function calls. So we had modularity in the code. We were doing better. And so we believe that one of the advantages of behavior trees is modularity. So we have decided this more neat, especially when it comes to very complex system. But not only that, since the behavior tree is stick-driven rather than event-driven, and the difference between that is going to be clear in the interactive session, we can have a goal-oriented and reactive behavior. And it's also modular. These three are very important when we have to design a reliable plan. In fact, as we can see here, we have that the same behavior tree that is very compact, it's very easy to understand. We can have two different action plans according to what is happening in the environment. So we have a very compact way to describe a fault-tolerant execution. But not only that, we also see that using behavior tree, it turns out that it's very easy to evaluate standard properties that comes from control theory. that are like finite time stability, safety, robustness, and chattering free. These are very important because our formal characteristics that we have, they are a must if we want to describe and design a high reliable system. This is also important, and we're going to see this and more tomorrow in the interactive session. We will see why Beaver 3 are somehow better than finite state machine. Thanks.
Hi, my name is Piotr Trojanek. I am research assistant at the University of Bristol. Together with Kerstin Eder, who is my supervisor, we wanted to gain confidence in the open source robot navigation software. We wanted to make sure that when we run the software, we will not get segmentation fault, infinite loop, or deadlocks. We looked at software from Player, which is written in C and C++, and we tried several different state-of-the-art tools for verification of C and C++, but this code was too complicated for them or required a large number of annotations which are quite difficult to maintain. So instead we translated the code into Spark, a language that is a subset of Ada, and it's used in development of safety critical software. Spark is often compared to style guidelines like MISRA C, but it's built on solid software engineering foundations like pure functions and strong typing. We carefully translated the code without using pointers and memory allocation. And the unique feature of Spark that we used was that all annotations were both used for testing and static verification. We found that Spark is quite well suited to robotics software. For example, multi-dimensional arrays, which are very useful in robotics, are natively supported during verification. And a lot of information required for the proof in Spark comes directly from the code, so you don't have to write a lot of annotations in your code. With this approach, we found bugs in open source robot navigation software. And we no longer trust that software is safe simply because it's open source. We found that language restrictions, testing, and static verification are complementary to each other. And for one of the algorithms, we fully proved that no runtime error will ever occur. And this proof was almost fully automatic. Finally, the performance of our code is very similar to the performance of the original code in C and C++. I'll be very happy to tell you more about our experience in verification of real-world robot control software during the interactive session tomorrow. Thank you very much for your attention.
Hello, I'm Damien Lyons, and I'll be presenting this joint work. Currently, robots are used to handle conventional explosive threats, though not with much autonomy. Weapons of mass destruction up the ante substantially, and increasingly autonomy is being demanded. We want to be able to provide formal guarantees for autonomous robots that are used in counter-weapons of mass destruction missions. We've extended the Georgia Tech Mission Lab Robot Mission Design Toolkit with a verification module called VIPARS. User-designed robot software is combined with pre-existing models of robots, sensors, and environments, and evaluated against a performance requirement to determine whether the combination will always achieve that performance requirement, generating a probabilistic description of the result of the mission. A very popular approach to handling automatic software verification is model checking. We expect in our application to see probabilistic software, emergent behavior, robot teams, levels of autonomy, and rampant uncertainty. All of these things exacerbate the key weakness of model checking, which is state explosion. So we've developed an alternate approach, and we argue this approach is more appropriate for robust software applications. The key novelty of the approach is its focus on extracting state generators rather than state. So the Mission Lab program is automatically or manually translated to a process algebra called PARS as a set of concurrent communicating processes, which are combined with selected library models of robots and sensors and a user-selected model of the dynamic and uncertain environment. In a key contribution, this network is automatically analyzed to extract recurrent information flows between the environment and program, as shown here, called flow functions. And these flow functions are used to build a dynamic Bayesian network, which is then used to predict the performance of the combination. We experimentally validate all our predictions from formal methods. In this two-robot mission, robots move to a series of consecutive waypoints, synchronizing with each other as they go, as shown in the overlay map and in the video. Validation used 100 trials, measuring the time and end location in each case. The results shown here indicate the close correspondence between predicted and measured times in the center graph, and between predicted and measured spatial uncertainty on the right. Future work will include missions with uncertain obstacles, heterogeneous teams and swarms, and user studies. And I'll be happy to give additional detail on any of this in the session tomorrow. Thank you.
Hi, my name is Jana Tumova, and I'm going to present a joint work with Alejandro Marzinotto, Dimos Dimaragonas, and Danica Krajnegic on maximally satisfying LTL action planning. So let me start with a general motivation to what we are looking at. We have a robot, and what we would like to do is to give it a complex high-level task, such as repeatedly survey some region, grab a ball somewhere, and then drop the ball somewhere else. And our goal would be to automatically control the robot to accomplish the task. So one of the ways how to look at this problem is a formal methods-based approach, as George introduced you. So our robot is abstracted, its capabilities, motion and action capabilities are abstracted as a transition system, and then the high-level task is formalized through some temporal logic specification, and our goal is to synthesize a sequence of actions that, if performed by the robot, would guarantee that the specification would be met. But the actions sometimes fail. The robots sometimes just don't do what we assume them to do, like here when the robot did not grab a ball. So that happens that the task might become infeasible. So our goal in that case, in this paper, is to synthesize a reactive plan to meet the specification as closely as possible. If it's not possible, do it fully. So as our model, we have a non-deterministic transition system. We have some recurrent tasks specified as a formula, and our goal is to devise a reactive plan, which is a history of the states that the robot goes through, the actions it tries to do, and successes or failures of these actions. And we would like to minimize the level of non-compliance and the distance traveled by the robot. So our main results is a discrete plan synthesis algorithm that builds on automata-based approach to formal verification. And as an output, we get an input-output automaton. That's our controller that we now need to implement. And we do that through behavior trees, which bridges the high-level controller with low-level robots controllers. And we implemented the solution in ROS and in this platform with narrow robots, and I will be glad to tell you more about our experiment tomorrow during the interactive session. Thank you for your attention.
Well, hello, my name is Bruno, and I'm going to be talking about planning for Markov decision processes using co-safe LTL specifications. So I'll start just discussing a couple of challenges that exist when we talk about mobile service robots. The first of them is, in general, you have uncertain actions, and we need to be able to cope with the failures in actions and this kind of stuff. Furthermore, we want to be able to specify intricate tasks in an intuitive manner, but also we want to have formal guarantees on the performance of our system. And another thing that we might want to have is allowing our user to add new tasks during the execution of, while our robot is executing other tasks. So our methodology introduces a way to generate cost-optimal plans which tackle these challenges. First of all, we tackle the uncertainty problem by using Markov decision processes to model our system. Then, to be able to specify intricate robot behaviors, we'll be using co-safe linear temporal logic. And also we'll be allowing for the addition of new tasks during execution by introducing on-the-fly replanning mechanism. So basically what we'll be doing is, what we do in our paper is show a way to generate policies that minimize the expected cumulative costs of generating a trace of our system that satisfies our co-safe LTL formula phi. Furthermore, we allow for addition of new tasks of this type and regenerate a policy that minimizes the whole combined task. This is more or less straightforward because we are using co-safe LTL as our specification language. And all of this, we extended a Prism model checker to be able to generate this type of policy and also the replanning part. In terms of implementation, we implemented this for robot navigation. So we built a topological, an MDP representing a topological map for a robot, where the nodes are these blue circles, and used the Prism to generate policies and implemented our execution and dynamic replanning mechanism, everything fully integrated in ROS, and this was running on a robot that was deployed for 3 weeks in a real office environment. That's it, thank you.
Hello, my name is Arun Kumar and I'll be presenting my work on Safe Robots framework that I did with Professor Bruno Monsos and Professor Adriana Tapus at Insta Paris Tech in France. Safe Robots is a model-driven framework for the design, development, and analysis of software for robotic systems. Our first objective is to identify the robotic domain-specific problems and requirements that are not explicitly captured in existing frameworks. We have classified these challenges into broad classes such as uncertain problem space because no systematic reuse-based software development process is adopted in robotics. And another one is the large solution space that exists in robotics with different non-functional properties for different scenarios. And the lack of design time context information, and the system designers assume something which are not properly documented in the model. And the last one is the inability to find the right level of abstraction in the software component, which is usually a trade-off between the usability and portability of the software code. For this, our second objective is to identify the core software engineering methods so as to address these domain-specific problems. Safe Robots is a model-driven toolchain that we are currently developing at our laboratory. It shifts the focus on software model rather than software code. In this framework, there are 4 conceptual spaces as shown in the figure. Specifically, knowledge space, problem space, solution space, and operational space. And there are several models that are associated with this in each space. In this paper, we are concentrated more on the solution space modeling. We have proposed a meta-model-based modeling language called solution space modeling language to model the solution space. Using this language, functional and non-functional aspects of the system can be modeled. The model is based on connectors and gates and connectors as shown in the example model. The connector represents the computational algorithm and has a non-functional property associated with them. And non-functional attributes and quality of service can be modeled using our non-functional meta model. In this way, the SSML language helps to capture multiple solutions in a single model. So once we have more platform-specific details and other context-related information are available, more specific constraints or non-functional properties can be applied on this solution to derive an operational model. The strategies allow to document and analyze these properties in a formal way. So to conclude, we have used 2 case studies. One is a simple mobile robot integration example, another is a vehicle tracking application in an industrial context. Our proposed framework, Safe Robots, raises the level of abstraction in which these robotic systems are designed. Solution space modeling language helps to model multiple solutions to identify the quality attributes and document in a formal way during the system design process. Also, we have proposed a non-functional meta model to model the non-functional attributes of the system. I'll be happy to explain more during the interactive session tomorrow. Thank you.
Hi, my name is Indranil Saha, and I will talk about automatic synthesis of multi-robot motion plan from safe LTL specifications. This is a joint work with Rattanachai, Ramai Tithima, Vijay Kumar, George Pappas, and Sonjit Sheshia. I'll start with an example. This is a top view of a three-dimensional workspace divided into rectangular grids. These are the initial location of 4 robots, and they have to move to their final location in the right side. And while the robots will be moving, they have to satisfy a set of invariant properties, and the properties are like this. They have to always be in a rectangular formation. They have to maintain a precedence relationship, that is, no robot can pass any other robot either in the x direction or y direction, and they have to maintain a minimum distance with each other. We have synthesized such trajectories automatically, and in this video, you can see that 4 quadrotors are moving using those trajectories, and they are satisfying all those requirements. So the goal of this work is to synthesize motion plan automatically for a group of robots with complex dynamics and complex specification. And in this work, the specification is given in a subset of linear temporal logic called safe linear temporal logic. Using safe LTL, we can capture properties that should always hold on the trajectories. Existing solutions for LTL motion planning mostly rely on discretization of the configuration space of the robot, which is computationally expensive and not very suitable for multi-robot systems. In our approach, we first develop a set of control laws that can be used to control the robots into defined configurations. And the closed-loop behavior of the robots under the action of these control laws are called motion primitives. We use an off-the-shelf SMT solver to generate these trajectories automatically by sequentially composing these motion primitives. We have developed a tool called Complan, which is available for download. And finally, I will show another example. Here, we again have 4 robots, and these first 2 robots have to move to anywhere in the location B, and the second 2 robots will move anywhere in location A, and they have to satisfy this minimum distance requirement. And here you see how the robots are moving, satisfying the requirements. And as future work, we are extending this work for full LTL. And thanks for your attention.
Hello, everyone. This is Jingfu Jin from the University of Texas at Dallas. Today, I'm going to give a short talk about a stable switch system approach to obstacle avoidance for mobile robot in SE2. This work is co-authored with Adrian Green and Professor Nicholas Gens. The motivation of this work is to reach a particular goal position while avoiding obstacle on the way to the goal position. We propose novel switched system approach to achieve the goal. We switch between obstacle-free and obstacle avoidance region. In each region, we derive repulsive and attractive vector. Then the regions determine the velocity vectors. We use the velocity vectors to design the control law and guide the robot moving toward the goal. We also propose novel switching signal. Switching signal 1 consider the distance between robot and obstacle and angle difference between the robot orientation and the bearing angle to the obstacle. Switching signal 2 is based on switching signal 1 and consider current switching signal and reduce the potential chattering. But the switching signal 3, like the traditional switching signal, only consider distance between the robot and obstacle. So in obstacle-free model, the robot will move along a trajectory vector like this. And in obstacle avoidance model, the robot will move along avoidance vector, which is perpendicular to the repulsive vector, and move along the and positively project onto the attract vector. The velocity vector actually represents either attract vector or avoidance vector. In our approach, we don't need to know the obstacle ahead of time, and also our approach doesn't suffer from local minimum. We also design control law based on step Lyapunov analysis, and we prove our system is asymptotically stable to the goal position. Since our switching signal considers relative distance and orientation, the avoidance region decreases while the angle difference is increased. We also show the angle difference always increase in our work. If we only consider the distance information, the switching surface keeps the same all the time. Our work also possible to extend to the multiple obstacle avoidance and collision avoidance.
My name is Evan Arbe. I'm going to talk to you about a specification language for constraint-based robot control, continuous control. In traditional robot applications, you have a fixed robot environment, you have limited sensing and limited variations. One of the aims of our project is to move towards fast deployment in human environments, where you have a much more flexible environment, increased sensing, such with force sensors, distance sensors, or cameras. And the task consists more than only trajectories and points. A typical solution for this is to use constraint-based optimization. In this approach, the controller solves at each time step an optimization problem. The subtasks at hand, such as following a trajectory or avoiding an obstacle, are then formulated as constraints to this optimization problem. The contribution of this work is to design a specification language for such controllers. In this way, by separating the specification from the implementation, we hope to improve on the reusability and the composability of these specifications. We also facilitate the work of the application developer, which is more of an expert on the application domain and less of an expert on robot control. And now I'm going to focus on a few of the innovative aspects of the specification language. And one of these aspects are feature variables. And these variables are additional variables that you can introduce to specify additional freedoms. This is in contrast to the constraints that only specify limitations. And for example, if you move on a trajectory, but you do not care where you are on a trajectory, you can use a feature variable for that. Another innovative aspect are symbolic expressions that are used for specifying the geometric relations. The underlying implementation translates these symbolic expressions to an expression graph, where you can do all kinds of operations on. And now I will show you a small example that shows you that you can already achieve complex behaviors with such controllers. In this example, the robot enter vector moves on two circular trajectories, but the trajectory on your right can vary its velocity. At the same time, we impose collision constraints, we impose joint position and velocity constraints, and the head camera follows the left enter vector. Keep in mind, this is a reactive controller, so it can also react on force interaction or other sensors. I thank you for your attention, and I hope to see you at the interactive sessions.
Hi, I'm Steve Hart. I work for General Motors and the NASA JSC Robonaut and Valkyrie teams. I'm here to talk about Robot Task Commander. It's our software front end for controlling and writing applications for the NASA JSC robots. The motivation behind developing RTC was we wanted a tool for expert and non-expert users to quickly program sophisticated behavior on humanoid robots of the complexity of Valkyrie and Robonaut with legs, whatnot, and we needed to be able to either adapt programs quickly in the field, like in a Valkyrie DRC disaster scenario type situation, or to have astronauts or crew members on the International Space Station where there is a Robonaut be able to change and build programs quickly. RTC roughly is a VPL that allows you to have computation nodes written in Python and to build hierarchical applications and process nodes out of these Python units and distribute them to various execution engines that you have available. So for example, you could write an application and distribute some computationally intensive image processing algorithm to one machine, but you'll have a single front end where you can deploy and get some feedback for the state of your application. We wanted to be not specific to something like ROS or YARP or ZMQ, but we wanted to allow the operator or user and developer to have and write plugins for whatever transport layer that they would like to use. And basically it comes down to writing your process nodes abstractly, only in terms of the input data types and output data types. And then when you use those computational nodes in your applications, you can specify that the input data is going to come from a ROS topic of a specific type or a YARP port or whatnot. We really wanted to make it plugin based, so it's lightweight, but the developers can really add and interface with whatever APIs their robot or situation needs. This is the main API. It allows you to write the Python applications and put them together in the VPL, store them to a library, and reuse them hierarchically. You can also write parameters and bind the input and output topic ports as you need to in your application and very quickly. And also set the deploy target for each of the individual nodes. Skip all that and show a little movie. And I invite you to come talk to me more about it, and we'll show you a little bit more. This is just a quick application of dragging and dropping some core movements from the Robonaut 2 application library, how quick it is to assemble these things up, connect them, and then hit play. All right, thank you, and hope to talk to you tomorrow.
So my name is Giorgio Metta, and presenting especially on behalf of Ali Pai Khan, who couldn't be here to present his paper. Our work is about the reusability of software modules, and especially on the iCab robot. So we have this framework where we can develop separate modules that are actually separate executables and connect them through objects called ports that take care of communicating data from one module to another. This is sort of a motivating example. Let's imagine we have a face detector that we develop. This can be, let's say, the OpenCV face detector, and we want to connect this to a head control module. Typically, you have to decide, for instance, whether the face detector is doing well, whether to track the supposedly face, or rather decide that the head has to search around or do something different. So you have a problem of deciding whether to put parameters on this specific application, but if you put the parameters or any other way of selecting whether to track or not in the modules, you constrain the reusability of the modules. So what we decided to do was to develop a way to upload a runtime scripts into the ports that is into the communication part of the application, and make these in terms of script, which means we can actually define them irrespective of the actual modules. So you can develop your own face tracker and then decide what is the specific threshold that you need for your application. Or this is a simple example. Of course, you can change any parameter that way. We did this through Lua, a specific scripting language. And this is uploaded into the port at runtime. It's important that it's at runtime because you can change them on the fly and doesn't require recompiling all your modules. And this is a possibility. Another thing that is often needed and that we solved in a very similar way is the ability to arbitrate between different signals. And this leads to, again, a Lua script that is uploaded into the port and can be used for deciding whether you selecting a signal from a face detector or rather another behavior that is look around. This brings you very quickly to the ability of designing behaviors, very complicated ones. And if you have time to come and see the interactive presentation, you will see a robot that cleans the table by reusing modules that we've taken from our repository. Nothing was developed specifically for this type of behavior. It's just a collection of modules and then a number of scripts that arbitrates the various modules. Come to see this tomorrow. Thank you.
Hi. Unfortunately, Andrei Ruzakov was not able to attend the conference due to visa issues, so I will try to give the presentation on his behalf. My name is Michael Blush. I'm also from ETH Zurich, and I'm more in robotics data simulation, but I'll try to give my best to present these results. So their work is on concurrency in robotics. Concurrency is something that you have very quickly as soon as you have more than one sensor or actuator in a robot. And ideally, a robot would benefit of the concurrency. However, it hasn't really been used extensively in robotics so far due to additional qualifications which are not that easy, and also additional pitfalls like data races or deadlocks. So the method they propose is called RoboScoop. It's a library which also allows the integration with other robotic frameworks like ROS, and it's based on the programming language Scoop, which has an object-oriented structure and allows the coordination and concurrency of tasks. It also allows to call external libraries like C, C++. So Scoop stands for Simple Concurrent Object-Oriented Programming. It is a natural extension of the programming language AFIL, and whereas it introduces the additional keyword separate. It allows an easy parallelization and synchronization of tasks, and by construction avoids data races. So if you have a quick look at a simple example, so let's say you'd like to implement a method called look, which uses three separate objects, a left eye, a right eye, and a ball. And so one tool of Scoop would be so-called wait conditions, which guarantee that the method is only executed once those wait conditions are fulfilled. Here you can also see the close correspondence with behavioral specification, which allow an easy creation and coordination of robotic tasks. So it has been applied and evaluated on different robotic platforms. Two of them are here. One is the SmartWalker and the other one is Tumio. Both are developed in partnership with ETH, and the SmartWalker is a robot for assisting elderly people, and the Tumio is used in educational programs. Yeah, so I'm a bit early, but yeah, if you have any further questions, you can visit the interactive session tomorrow morning. Thanks.
Hi everyone, my name's Daniel Lafaro. I'm from the Lafaro Labs at George Mason University, and this work was done with Will Hilton and Youngmoo Kim at Drexel University, at the Drexel Autonomous Systems Lab and MET Lab. We worked on a lightweight, cross-platform, multi-user robot visualization system using the cloud. Now I ask you, have you ever had a robot, one robot, and you had an experiment that was going on, and everyone wanted to watch? Now they all had good reasons for this too. So someone had to watch for the safety of the robot, someone had to watch for the foot placement in this case, someone had to watch the vision, someone had to watch the balance, someone doing the IK, etc. And everyone's huddled around this one computer that's controlling and monitoring the robot. That's not feasible for most systems. So what's the solution to this? Well, we simply allow everyone to see. But in doing this, we have to make sure that it does not affect the robot's bandwidth utilization. It has to be very accessible, so that means no custom hardware or software required, so everyone would be able to use it. And it also has to be intuitive. So what did we make? We based it on a internet browser-based system that you can monitor the robot's state, errors, as well as actions live in any browser. So that means it's Windows, Mac, or Linux compatible, and also on your mobile devices. Now this is a very important thing for when you're in the field and you don't want to carry around a laptop if you just want to monitor a few states of the robot. Now how do we do this without affecting the robot's bandwidth? Well, we run it on the cloud. Two clouds, in fact. We have a private cloud and a public cloud. The private cloud is the robot's network. We have a process-based system which all the states get sent off to one main computer on the robot's server, and then when anyone wants to check that, they simply talk to this desktop-based computer server-based system, so it does not affect the robot's bandwidth. If someone off-network wants to see, it's published over Firebase, so only one set of data is going out, and an amount of users can use the system externally. So this is compatible with multiple robots. We've done it with DRC Hubo and Hubo 2 Plus, multiple browsers. And I invite you guys to come for the interactive session for a live demo of this system. So bring your WebGL capable device, including laptops and multiple devices, and hook it up to our network and check out the robot in action. So thank you.
Hi, my name is Cui. I'm from Purdue University, and today I will introduce a refresh a self-adaptation framework to support fault tolerance in field robots. Let's look at two multi-robot scenarios. In the first scenario, we have two robots, each consisting of cameras mounted on manipulators. And they are performing a task to detect 3 targets and label them. Initially, all time-based and port-based object components are all running on the robot 2. But let's suppose fault comes in and degrades the camera 2's performance dramatically. In order to accomplish the task successfully, the system should generate a new task solution and self-adapt. And we can imagine there are several potential configurations, such as the robot 2 can migrate some port-based object to robot 1, or the robot 2 can migrate all the tasks on robot 1, or the whole task can stay in the robot 2, but the robot 2 can get the new image processing component and in order to finish the task. And in the second scenario, we have 3 robots to accomplish the same task, and R1 and R2 are the same as before, and we added a third computational node. The initial solution remains the same. Suppose in this case there is a resource deficiency where the battery on R2 is depleting. To conserve the power, the system may migrate some components onto R1 or to R1 and R3. Or the system it may come up with more optimal solutions. So in such unanticipated situations, so in order to let the robot team accomplish a task successfully, and we should let our system to self-adapt. So refresh wanna provide infrastructure support for the system to dynamically generate feasible task solution candidates and decide which is the optimal one. In summary, the refresh is an integrated self-adaptation architecture, and it also supports heterogeneous wireless networks. Thank you.
Hello, everybody. My name is Lynn Marques, and I'm presenting this collaborative work on speeding up rollback localized particle filter SLAM with a multi-threaded architecture. The motivation for this work was running SLAM algorithms on very cheap computing platforms like that Odroid processing board containing a quad-core ARM, or the PC containing an Intel Atom dual-core processor. One of the most popular SLAM algorithms is G-mapping. We analyzed G-mapping, and we concluded that more than 98% of the processing time is spent on laser scan matching. Analyzing in detail that part of the algorithm, we concluded that that processing is mostly independent of each particle processes does its process independently of the other particles. So we parallelize that part of algorithm using an open MP approach. The code is available on the link below. If we compare the results obtained in the single-threaded version, the publicly available one, with the proposed multi-threaded version, in this case for the ACES building, that's a popular data set, we can see that in the upper graphics obtained with a profiler, one of the cores is all of the time fully processing, so there are no time remaining for other processes, and there are some loss in the process that conducts to errors in the generated map. In the multi-threaded version, we see that there are still some available processing time, and we can run a larger number of particles without errors. When we compare, we obtained speeding ups of about 2 in the hardware that we tested, and significant results in terms of accuracy. Thank you.
My name is Jürgen Rossmann, and I would like to present the e-robotics approach on the development of intelligent robot manipulators. First of all, what do we understand by e-robotics? E-robotics is a term that was coined in the field of e-systems engineering, so it stands in line with terms like e-business, e-health, e-government. And basically, the E stands for the extensive use of electronic media to facilitate the development. And of course, simulation and virtual reality technology plays a key role. But e-robotics is more than just simulation, because this is a simulation approach which usually focuses on one specific aspect. If you take this a bit further to a virtual testbed, you integrate various processes under one software hood, if you will. So this comprises rigid body simulation, sensor simulation, terra mechanics, and so on. And if you add further capabilities like analysis and, on the other hand, commissioning and deployment support, then you are with an e-robotics application. So far, the major scientific challenges are in the combination of the various processes. For example, for such an application, you need to deal with orbital mechanics, propulsion simulation, the different sensors, drivetrain simulation, and so on. So to do this under one software framework is a major scientific challenge. So far, we're doing it for the International Space Station, for example. Robotics on the International Space Station can be dealt with. We're doing it for planetary exploration, so this framework is already in place and works quite well. We're doing it for flexible automation, and one of the new features is to integrate hydrodynamics and fluid dynamics with robot manipulators. And this is fairly new and interesting, and the theoretic framework that covers it is pretty new. Actually, altogether, we've developed more than 30 different applications in this field. And in the paper and in the talk that I'll be presenting, or in the discussion that I'll be doing tomorrow, we'll be talking about how we integrate robot manipulators into these various application fields. And as I have 30 minutes left, I can focus on this last question. What is the difference between the two videos? Well, for the developers, the difference is none, because you can develop against the physical system as well as against the simulated system, which behaves pretty much the same. But for the investor, the difference makes 130,000 euros. And I'll be happy to talk about this with you tomorrow in the interactive session. Thank you very much.
Hi, I'm Guido de Kroon, and today I will present a project I did with the European Space Agency, and it's about the first crowdsourcing experiment using real robots. So our idea was to make a game for the Parrot AR drone that people would play just for fun at home, and in the same time they would be gathering data for our experiment on visual obstacle detection. So this is the concept. On the top left, you see that there's a smart device, in this case an iPhone, and the player controls the drone with this smart device. And in the same time, the drone is detecting a marker that is delivered with the drone, and this detection allows us to estimate the 3D state of the drone and the orientation with respect to the marker, so that we can render an augmented reality on the smart device. In the same time, this also allows us to get a ground truth measurement for our experiment on obstacle detection. Now, after the player is done playing, the images that were made during the flight are being processed, so surf features are being extracted, and if the player agrees, these surf features are sent over the internet to our database, which we then can use for data mining and analysis. So this project was as much about game design, testing, and release as it was about the experimental setup. And the main challenge was to align all these things and do these things while you're not used to it as a researcher. So we released this game in March 15, 2013, and luckily we had a lot of media attention ranging from BBC Technology to RoboHub, which allowed us to interest players in this game. And since that time, there have been 20,600 downloads, people playing this game, and 1,500 uploads of data samples. Now, concerning the analysis, I think it's nice to mention that in this crowdsourcing experiment, we do not control how people play this game. So if you do an analysis that does not need ground truth, you can just use the whole set. But if you want the ground truth for example, the obstacle detection, then you need to down select, for example, to cases where the marker is detected. This is a preliminary result in which we see that if the distance gets lower to the left, then the number of features extracted from the image gets lower as well, which can be used for obstacle avoidance. Now, finally, I did not bring a drone with me to have you play it, mainly because I want you to go home and play it yourselves, actually. So to do that, please go to this website, astrodrone.org. It's available for iOS and for Android. There's now 2 levels, and yeah, if you have questions about this project, the do's and don'ts of doing such a crowdsourcing project, please come tomorrow morning to the interactive session. Thank you.